Okay, hi and welcome to lecture 2 of the Fluid Mechanics Primer, where we're going to look at the Advection Diffusion equation. I'm going to start this lecture with a definition of diffusion, and in what follows we're going to assume that diffusion is something which can be written as a flux of a quantity that's proportional to the gradient of that quantity. So if I have a tracer with a concentration C sitting in a fluid, then a diffusive process is one in which the flux is proportional to the gradient. Or, more strictly speaking, we'd write flux is equal to kappa times the gradient, where kappa is the diffusivity. We normally think of diffusivity as being a molecular process and a consequence of Brownian motion, and it's equivalent to laws for heat conduction. In 3 dimensions, of course, this flux here becomes a kappa times grad C, where grad is a vector, and for a 3-dimensional fluid, this here is the form that we're going to use. So what we're going to do, following on from the last lecture, is we're going to assume that we have a control volume, V, and there's a total amount of some tracer within our control volume, and we can find that total amount of tracer by integrating over the volume. We're going to assume that this tracer is conserved, and that means that the time rate of change of the total amount of tracer in our control volume is simply equal to the amount of tracer which is diffused in from around the boundaries. In other words, if we integrate over the whole surface, we take the flux that is normal to the boundary, as in grad C dot n ds, and we integrate right around our control volume, and this is an expression for saying that the amount of tracer which is in our control volume only varies if we put more tracer in or take some tracer out by this diffusive process. So this is a lovely integral equation which we've now got to do something with, because as mentioned in the last lecture, these equations are much easier to deal with in point form. So to get to this, I'm going to go through very similar steps that I used for the last lecture. And first one of these is I'm going to apply Leibniz in 3D, and that's going to be applied to this left-hand term. That means that I can bring this time derivative inside this bracket, this integral, and I'm left with an area integral around the edges, which is just simply C times U dot n ds. Okay, and the right hand side is still unchanged. Okay, so now we've got 2 area integrals and a volume integral, and once again, sorry, I'm just going to have to grab out the underscore under that C. Once again, we're going to apply Gauss's theorem, or the divergence theorem, to turn these 2 integrals back into volume integrals. And so the way we do that is we integrate over the volume, so this first term is unchanged, and we now have an integral over this volume of the divergence of C times U. Okay. And on the right hand side we end up with the divergence of kappa times grad C dV. Okay. And as before, by this equation you can see here is integrated over a control volume of arbitrary size, which means that we can make it infinitesimally small. And if that's infinitesimally small, then it converts straight into point form, and we end up with an equation which just has a time derivative, a divergence of the concentration times velocity, and a divergence of the diffusive flux. That's kappa, sorry. Okay, so this is now getting close to the form we like in an advection diffusion equation. For here I'm going to make a couple of simplifications. The first one is I'm going to assume that this kappa here is constant, and so the right hand side becomes kappa c times grad squared of c. So this is just a Laplacian on the right hand side, which will be familiar to you if you've done heat conduction before. And the next thing I'm going to do is I'm going to expand out this term here on the left into by the product rule to give a u dot grad c plus a c times the divergence of u. Now if we're working in an incompressible fluid, we know that the divergence of u is equal to 0 from our last lecture. So for an incompressible fluid we get the equation dc dt plus u dot grad c is equal to kappa times grad squared c, and that is an advection diffusion equation. From here we can manipulate this in two ways. We can, if you like, shrink it down by using the total time derivative, and this looks like a simpler equation where we're basically following particles, and this total time derivative now includes the advection and the local rates of change. The other thing I want to point out to you is just what happens when we pull out all the components of this and get rid of the vectors. So that means I'm going to expand it all. I'll go right over to the left here. I still have the time derivative, of course, but this u dot grad expands out to u times dc dx plus v times dc dy plus w times dc dz. Okay, where u, v and w are the lateral and the vertical velocities. And then we also have, on the right hand side, kc times d squared c dx squared plus kc times d squared c dy squared, and we have the same with d squared c dz squared. So the reason I'm doing this is just to show you how these terms all expand out, and particularly how this advective operator works. So the key thing about the advective term is that the local concentration at any point on the left here, let me underline that in red, that doesn't change unless there's if we forget about diffusion for a moment, the local rate of change doesn't vary unless there is both a gradient and a velocity to the fluid. In other words, you can have a gradient in a fluid, but if there's nothing moving anything around, you don't get advection. On the other hand, you can advect everything you want, but if there's no gradients, then that doesn't produce any change. So it's the product of the gradient with the velocity that gives us the local rate of change. If we just look at the diffusive part of the problem, then what you can see is that even if there is a gradient, and if there's a gradient there's a diffusive flux, that still doesn't cause any local rate of change of concentration. You need a curvature in the gradient, and it's this curvature in the gradient which tells us, which gives us a divergence of this flux, if you like, and causes a rate of change. In other words, if you have a small volume and you're diffusing material in from one side, but you're diffusing it out on the other side at exactly the same rate, then you have no net change of concentration in that small volume. On the other hand, if you're diffusing fluid in but you're not diffusing anything out, then you have a flux divergence and you can get a local rate of change. So I'm going to stop there with this video, and we'll pick it up in the next one with stress and the momentum equation.